Compasses drift. Satellites glitch. Auroras flood the equator. Deep beneath the surface, Earth's core has gone silent, and the invisible shield protecting all life has begun to collapse. The question isn't whether you'd notice, it's how long you'd survive. 2,000 miles beneath the rocky mantle lies a fluid shell of liquid iron and nickel, 2,200 kilometers thick. Driven by planetary cooling and rotation, this churning metal acts as a massive electrical generator. This is the Geodynamo, a mechanism first mapped in 3 dimensions in 1995 by scientists Gary Glatzmeyer and Paul Roberts. Their calculations revealed how these liquid currents sustain the magnetic shield protecting our atmosphere. If the core's motion halted, the shield would not vanish instantly. Instead, it would begin a slow terminal decay. Without active regeneration, the field would fade over centuries, governed by a natural magnetic diffusion timescale of 10,000 to 100,000 years. Yet even a progressive decline of 5% per century would trigger a cascading collapse of the systems that keep human life alive on the surface. The first signs of this decay would be quiet, creeping across the globe without a sound. High-precision navigation charts, updated annually, would begin to drift as magnetic poles wander unpredictably. When the field strength drops below 10 microteslas, mechanical compasses lose their pull. The needles wobble, succumbing to friction and thermal jitter, rendering the planet's oldest navigation tool useless. But the crisis reaches far beyond human technology. Sea turtles, navigating open oceans, fail to find their nesting beaches. Migrating songbirds, like the European robin, lose their internal maps, driving a sudden wave of vagrancy where millions of birds stray hundreds of miles off course, flying blindly into a world that has lost its coordinates. Above the atmosphere, the boundary of safety rapidly contracts. With the magnetic shield fading, the magnetopause moves thousands of miles closer to Earth, exposing low Earth orbit to a relentless tide of solar radiation. Satellites now swim through a dense flux of high-energy protons. These particles easily penetrate metal hulls, triggering single-event upsets, ghostly bit flips that corrupt onboard microprocessors and scramble tracking systems. Simultaneously, intense electron clouds build static charges on solar arrays, threatening catastrophic electrostatic discharges. This orbital instability cascades downward, bringing the vulnerability closer to the surface. As the ionosphere becomes turbulent, GPS signals refract, generating position errors of tens of meters. The invisible synchronization of global aviation, maritime shipping, and logistics begins to steadily fracture from the top down. The decay of the magnetic shield brings the danger down to the surface, targeting the high-voltage grids of the built world. Geomagnetically induced currents are quasi-direct electric currents driven through the ground and into metallic infrastructure during space weather events. Long-distance power lines act as massive antennas, funneling these currents directly into high-voltage transformers, saturating their magnetic cores. The single historical analog occurred on March 13, 1989, when a severe solar storm collapsed the entire Quebec power grid in just 90 seconds, leaving 6 million people in cold darkness. In a weakened magnetic environment, this collapse becomes a global norm rather than a rare anomaly. As the lights go out, the threat moves closer, targeting the human body as the next frontier of risk. The threat to human biology does not strike everyone at once. Astronauts aboard the International Space Station feel it first, exposed to raw space radiation as the Van Allen belts decay. Their daily doses quickly climb toward career limits. Closer to the surface, commercial aircrews on high-altitude polar routes face the next wave of exposure, where incoming particles funnel through the thinning field at the poles. Yet the danger remains highly unequal. At sea level, the thick blanket of the atmosphere still acts as a reliable shield, preventing instant catastrophe while the threat slowly descends. But this atmospheric shield is not invulnerable. As the magnetic field decays, solar winds begin stripping away the upper atmosphere through ion sputtering, slowly bleeding oxygen and nitrogen into space. This is the fate of Mars, which lost its global dynamo 4 billion years ago, leaving a thin, barren remnant. For Earth, this erosion is a slow drain, unfolding over centuries rather than days. Yet, incoming solar particles disrupt ozone chemistry, thinning the ozone layer and allowing harmful ultraviolet radiation to flood the surface. Soon, survival on this exposed planet will require looking downward toward engineered spaces built to withstand a hostile sky. Underground shelters buried beneath 10 meters of rock reduce charged particle exposure by 90%. Within these subterranean sanctuaries and steel Faraday cages, sensitive microprocessors and critical communication systems are preserved. On the surface, grid hardening and transformer blocking devices offer practical, partial defenses against the celestial onslaught. Yet engineered barriers have absolute limits. No bunker can salvage global logistics, secure industrialized agriculture, or prevent the collapse of modern finance. Physical survival remains possible, but the complex fabric of civilization becomes dangerously fragile. If the invisible shield protecting our planet disappeared, how long would humanity survive? Deep beneath us, the engine of life continues to turn, for now. If the invisible shield protecting our planet disappeared, how long would humanity survive?